This lecture series is actually part of the Design and Technology Initiative that Jenny Sabin and I co-chair. And you might have heard some exciting news around design and technology. Design and tech is actually one of the radical collaborations that Cornell is sponsoring on a university-wide level. One of the things that we get asked a lot is what is design and tech? And we actually think what design and tech is a lot about what the people who are doing design and tech make it. But that is one of the impetuses for the lecture series, that we actually get all these different views of cool things that are going on at Cornell in this space. And so I'm really excited to introduce Harald Haraldsson, who is the director of the XR Collaboratory here. Harold's actually the first person who's actually giving this talk from Cornell Tech, so that's very exciting. His talk is going to be on designing and prototyping 3D interactions for augmented and virtual reality. His work is now like really in this very hot space all of a sudden, with like Meta turning his like redirecting the whole company around things like that, or in the area that he's been working in for quite some time. And so I'm excited to have him give a talk. And with that, I'll let you go.
Thank you so much, Wendy, and thanks to the organizers for this series. Now let's just make sure that we have the right screens. All right. Zoe, are you seeing anything?
Harold, we are seeing you, your video right now.
We need better design of this technology.
See what I had a visitor from Google today, and I was remembering that Google is click on your meeting.
So I don't know why this is now blank. Let's see.
It was just working earlier.
Yeah. Let's see. So we had an IT here before 5 to set this up, and now they're gone. Hold on.
It looks like you're screen sharing now.
Okay.
We can see your background.
There we go.
Yep, looks great.
All right. Still up there?
Yeah.
Okay, perfect. Let me set this up. So as I was saying, thanks, Wendy, for the introduction, and thanks to the organizers for putting this together this semester. Really looking forward to seeing what this initiative turns into and the next series next semester. So as Wendy said, I'm the director of the Exart Collaboratory, where we work with faculty, students, mostly master students, and other researchers on a variety of XR-related projects. I also teach 2 courses on the topic of AR and VR here on campus in New York City. Now, before I start, I just wanted to clarify the intended audience for this talk. So I'm hoping that there are a lot of people here in the audience that are interested in XR design and development, but maybe not with like deep hands-on knowledge on that particular field. And the objective with today is to give a high-level overview of how we can design for 3D user interfaces and how we can prototype these designs. So this is a slide that I always use on day 1 in our fall course. So I'm going to read through this quote. Within another 25 years, we should be able to wear a pair of AR glasses outdoors to see and interact with photorealistic dinosaurs eating a tree in our backyard. So this is from a paper by Ronald Azuma, who is a well-known researcher in the field of AR. And what I always ask my student is, when was this published? Right? And I would like to get some answers to that question. What are your thoughts, Greg?
I'm gonna guess at least 2005.
2005.
1980.
1980s. Wendy?
1995.
Ooh.
1985.
Okay. So usually I get answers from maybe the 60s or last year and so on. This was actually published in 1997, right? Wendy, the winner for today. And the paper is called A Survey of Augmented Reality, and it's actually the most cited publication in this field. And the question is, do we have photorealistic AR dinosaurs in our backyards today? We're actually getting close. We have head-mounted displays that are capable of rendering quite realistic content, but maybe not quite. And what is actually interesting is that this is the first time I bring this slide up in 2022, which means that we're exactly at the 25-year mark. Usually when I've been going through this slide in the last 3 or 4 years, we're always getting closer to that mark. So the question is, where are we today? So for AR and VR, we could say that by far the most popular manifestation of AR is the handheld form factor through video see-through. So we have some really good utility applications where you can place virtual furniture instead of going to the shop and bringing that back to your apartment. And then on the virtual reality side, we're quite further along there in terms of consumer adoption, actually, of head-mounted displays, especially. So here's an example of a game called Beat Saber, which is one of the mega hits of the current generation of VR experiences, generating millions of dollars in revenue. So this means that there are product designers, entrepreneurs, researchers thinking about how do we design and how do we develop products or experiences for these platforms. And that is what we're going to talk about today. So first, let's go through the title of the talk. And by doing that, I want to explain the difference between 2D UI and 3D UI. So we have this word here, 3D interactions. So interaction or interaction techniques basically are methods that we use to accomplish a particular task through the user interface. So this means that in here we are talking about 3D UIs, and that is sometimes referred to as its own research area, 3D UIs. Now, taking a very kind of simplified look at the difference between 2D UIs and 3D UIs is not quite as clear-cut as we're showing it here, but for sake of simplicity, we'll do it this way today. We can think about 2D UIs as something traditional like the mobile phones when you're using it in a non-AR setting, and then when you're using, let's say, a desktop computer with traditional input devices like keyboard and a mouse. 3D UIs today in this talk, we're referring to head-mounted displays that have the capabilities of providing physical spatial input. So whether it's through hand tracking or dedicated tracked input devices, as you see here. So this also brings us to augmented and virtual reality. I assume many of you are familiar with the differences. If not, on the top photo there shows an optical see-through head-mounted display, which is an AR, which combines virtual content and the real world through an optical combiner. And then below that, we see a virtual reality HMD, head-mounted display. With that, you're completely immersed with virtual content, and you don't see any of the real environment surrounding you. And then design and prototyping is the last component of this title. And by explaining that, I just want to show this life cycle diagram here. There are many of these diagrams in the literature. This one is called the wheel. And as always, you have the analyze stage where you are trying to understand the user's current activities and their needs. You gather requirements. Then you move on to the design stage. And that, in our case, involves designing interaction concepts. And then the third stage on this life cycle here is the implementation stage. And that involves realizing the design concepts from the previous stage in the form either of prototypes or fully functioning systems. And then you move on to evaluate, and then you kind of go through the cycle again, and you can also iterate between individual stages. Now, today, we are talking about prototyping and not fully functional systems. So we can more or less just swap out the word implement for prototype in our case here. And we're going to focus on these two stages. We're not going to talk about analysis or evaluation today. Now, I want to frame this talk about an actual project that we've been working on with a number of faculty and students at Cornell Tech, and Weill Cornell. And this project is called Exart Care, and this is a healthcare related Exart project. So this Exart Care system supports a local caregiver who is co-present in a shared physical space with a patient and a remote clinician. Now, as with all remote collaboration, the communication space is virtual, and participants must therefore rely on technical mediation for communication. So we use technology to allow the local and remote sites to communicate. In this particular project, the local task environment is captured with depth sensors. So this synchronized depth and color data is then reconstructed into a real-time 3D representation of this local task environment. And this includes a live 3D representation of the caregiver and the patient. Now, this means that on the remote side, the remote clinician uses a virtual reality headset to interact with this real-time 3D representation. The local caregiver is equipped with an optical see-through head-mounted display, which overlays virtual content on top of the real environment. So we have VR on the remote side and AR on the local side. Now, as the local caregiver seeks guidance from the remote clinician on, let's say, a specific task, the clinician is able to create 3D annotations, which are then rendered in the field of view of the local caregiver. So this is, not a simple system to prototype, and we can break it up into remote and local setting. And the prototyping that we do actually takes place in a single lab environment. We have two researchers playing the roles of the local caregiver and the remote clinician. And we're using depth sensors and head-mounted displays, as we mentioned on the previous slide. So just to show you how this prototype looks. So here you can see the local and remote setting as implemented in this particular prototype. On the left, you have the local side, and on the right, you have the remote side. Now, the remote clinician is able to annotate the live 3D representation of the local environment, which is then visible to the local caregiver as virtual content through the optical see-through head-mounted display. And we also see that the remote clinician is represented by an avatar, and as well, the hands are also represented by hand models, creating the opportunity to share non-verbal cues this way. That would be really hard to do through regular video communication, and of course, impossible with just voice communication. So this brings us back to the life cycle and the prototyping setup. And this is what we're going to talk about today. How do we do the design and how do we do the prototyping for a system like this that includes two separate versions of 3D UIs, because we have VR on one side and AR on the other side. And these are actually a little bit different 3D user interfaces. Okay, so then we get to the design stage in our life cycle. And we're assuming here that we've gone through analysis, we've gathered all the requirements and so on, and we know something about our stakeholders, and in our case, the patients and the caregivers and the professional clinicians. When we design for 3D UIs, we can actually apply a lot of concepts from 2D UIs. So we have this really famous 10 usability heuristics for user interface design. This is by Nielsen. It's from the 1990s. It's on 2D UIs, but this actually applies to current 3D UIs as well. And when I go through this list with my students, we go through every single 10 points and we talk about it in the context of 3D UIs. As an example, visibility of system status. This is very important, whether you're using a 2D UI or 3D UI. The system should always keep users informed about what is going on. You should give feedback to the user within reasonable time. Another important thing here is consistency and standards. The key word, or the key phrase that I always use is follow platform conventions. In VR, that can be a challenge because these conventions are kind of all over the place, even still nowadays. But over time, there are some conventions forming, like which buttons are mapped to certain actions and so on. So we need to follow these. So this is just to show you that we can apply certain concepts and knowledge from 2D UIs to 3D UIs. The question is, so what are we actually designing? Looking back at the Exart Care system overview diagram, we might think that, well, we have a lot of features that we could implement. We could think about how these annotations are created, how the remote clinician moves around. There are a lot of higher level features and application specific tasks that we could jump right into and start designing. But I'm going to talk about more like lower level universal tasks, which are often used in this literature. And I'm going to simplify things just by looking at the VR component. We're not really going to talk about AR component for the rest of this talk. Now, these lower level tasks that I mentioned are selection and manipulation, travel, and system control. So you can create more complex tasks or application-specific tasks by combining these together. But we want to understand how to design and how to use existing low-level tasks for our own design. So I want to go through these tasks and talk about some of the techniques that are well known. So within the selection and manipulation, we even go further and we talk about these canonical manipulation tasks. So we have selection. So this is the task of acquiring or identifying a particular object. The real world counterpart to that would be grabbing an object or pointing at an object, right? The next one is positioning. So this is the task of changing a 3D position of an object. So real world counterpart would be, I'm moving this box here over here, and so on. We have rotation, we can rotate things. And then this does not really exist in the real world. I'm not able to take this box and scale it, at least not yet. So we then think about these canonical manipulation tasks. But one thing we should consider when designing techniques that solve these tasks are the parameters of each task. And these can be different from task to task. So for example, for selection, you have distance and direction to target. So you want to select an object in your virtual environment. The target size matters as well. Density of objects around the target. So let's assume that the figure here on the right shows a red object here in the center, which is our object of interest. Now, the interaction technique we might design to solve this task would change if there are no other objects in the virtual environment, right? So these are the task parameters. Number of targets to be selected. Are we selecting just that single object, or are we designing a technique that is able to select multiple objects? And then target occlusion. Is it actually occluded from our field of view? And so on. Similarly, for positioning, you have distance and direction to initial position, target position, the actual distance that you're translating that object in the virtual environment, and then also what is the preferred position of that particular positioning task. So we could drill down into all these task parameters, but I want to highlight the first one for each task. So distance and direction to target. Actually, distance. So we can split this into two parts. One is if the distance to the object is beyond arm's reach, and the second one is if it's within arm's reach. And let's start with that. That is a very simple case, and the very straightforward technique for that is called virtual hand technique. So that is just a directional mapping of the user's hand motion. So you either hold the controller or we're using hand tracking as input, and we just do one-to-one mapping, and the hands are being rendered here as they appear. This is a one-to-one mapping to establish this direct correspondence. Now, what happens if this particular box here is in the virtual world, is further away from me, but I really want to grab it, but I would prefer not to walk over there. Now then we need to think about techniques that allow that. And the most famous, the most basic technique is Gogo. The Gogo technique basically allows the user to extend the arm beyond their actual physical length. And that is done by defining a threshold. When you reach beyond that threshold, you move from the one-to-one simple virtual hand mapping to a non-linear mapping. So this means that you are able to extend your hand, and you're able to grasp and grab objects. So here's an example of an implementation. So the light gray controller represents the real hand, and then the virtual hand would be the black controller. So as you cross that threshold, the mapping becomes nonlinear. Now we're getting into pointing metaphors. And actually you see a lot of metaphors, and for design representation, metaphors are really useful to communicate what the technique is about. So I think I have a few slides here on pointing metaphors. Ray casting is super simple. It's just like that laser pointer that I'm holding here. So this allows us to select an object at a distance just by casting a simple ray and letting the environment to detect when that ray hits any object, and then we might attach that object to the end of the ray, and so on. So this is a powerful selection technique, except when high precision is required and the objects are either small or very far away. Pointing is not very good for manipulation because you're limited for, in terms of rotation around the axis of the directional vector. So, and we'll talk about that in a moment, how we should combine pointing and grasping metaphors for full manipulation. So here's another quick example. Again, basic techniques. This one is called fishing reel. And here it extends the simple raycasting because we want, let's say we want to change the position of that object we just selected. So this capability of reeling in the object along the vector actually gives us quite a good flexibility in terms of positioning. Now, the last one I'm going to talk about here in terms of pointing metaphors is the flashlight technique. And this essentially, as you see here, defines a volume and whatever objects that are inside the volume being selected. So this is good if you want to select multiple objects or small objects, even when they're far from the user, because this is obviously more forgiving than a single ray. And finally, jumping just briefly into a different category of metaphors, this is bimanual metaphors, and this is when we're actually using both hands. So what you see here, this is called the spindle technique for selection and manipulation. This cube here that you see at the beginning of this loop is essentially the cursor or the primary point of interaction. So when that cursor crosses or enters an object, that object is up for selection and manipulation. And then you can move your controllers around to rotate the object. You can rotate around 2 axes. We don't have roll in this implementation. And you can also scale. You can scale this object by changing the distance between the 2 controllers. So some design guidelines for selection and manipulation. There's no need to go out and design your own, let's say, existing manipulation techniques. There are a lot of these basic techniques that you can use and you should be using. Use task analysis. So look at the task and look at the task parameters and try to find your appropriate technique based on that. And then, as we saw for the Gogo technique and some of the others, is that non-isomorphic techniques are quite useful as well. That means that we don't have that one-to-one mapping for our input devices. And good rule here is to use pointing for selection and then grasping techniques for manipulation. But there's no single best manipulation technique for this category. Okay, I want to move towards travel. So travel, if we think about that in the context of our VR, our remote clinician who's wearing VR to interact with the local caregiver and the patient, how can we allow this user to travel from A to B in the virtual environment? Let's say the user wants to change viewpoint, wants to walk further away or closer to the subject, and so on. Well, nowadays it's quite easy to say, okay, well, we'll allow the user just to physically walk over there. Our consumer devices nowadays are standalone devices with really robust tracking, so we don't really have any limitations in terms of that. If we have the physical environment to do so, which is not always the case, the clinician might be sitting down at a desk or in a cluttered lab environment and not able to walk. So we need locomotion, and that is an interaction mechanism for moving the user within the virtual environment while remaining fixed or in a much smaller environment in the real world. So these are techniques that allow us to explore the virtual world without having to run physically all over the place. Now, the obvious approach might be to say, okay, I'll just do like we do in all these video games. We just move around the space, no worries. But remember that for VR, we have these displays strapped to our heads, and the stimuli is really strong. So what you get here is a really strong stimuli coming from the environment here to your visual sense organ, and that is not in line with what the rest of the body is telling you. So this is problematic. This would not be great for your clinician or for your VR user. You might have experienced this even if you have never tried VR, if you sit in front of a large TV and you're playing a game like this. So just a quick note on the vestibular system. We actually do spend some time on talking about physiology in our courses to teach how things actually work. But these are organs that are able to sense linear and angular accelerations. And if you're not moving around similar or in the same way as the visual stimuli is telling you, you have mismatched motion, and this can cause vection. So vection is what we call an illusion of self-motion that is purely caused by visual stimuli. And this can mean that we trick the brain into thinking that we're moving, but we're actually not moving. The bad thing here is if the vestibular system tells you that nothing is happening. This can cause sickness, dizziness, and worse. So what can we do? Well, another simple approach is to do teleportation. So this basically means that we allow the user to select a target position and instantly teleport over there. So this is at the other end of locomotion techniques than the continuous movement. This also has some downsides. The main one being that in terms of wayfinding, the user does not learn the spatial arrangement in the same way as if they would move continuous throughout the environment. So a lot of the work that you see within travel, and it's a very active research area, is how to combine the benefits of continuous movement and teleportation, primarily through some vection reduction strategies for continuous movement. So adding vignettes and so on. All right, I want to go through system control. So system control is the third category of these fundamental 3D interaction tasks. And if we put that in the context of the clinician, you might think, well, how can we enter text or retrieve files, mute the verbal communication, or maybe even undo some of these annotation activities? So these are examples of system control tasks. And for 2D, you can see here examples of system control elements that could be pull-down menus, pop-up menus, toolbars, and so on. Doing this in 3D UIs is not straightforward. And just taking what exists in the 2D world, bring it into 3D UIs is not always a recipe for success. For example, how we create these slides in Google Slides, you can see all these menus and the menu bar here. So imagine if you had to create a VR slide application, there are a lot of system control considerations you would have to solve, right? In a way, you can say if you have enough buttons, you could solve it, right? That's basically what a keyboard is. It assigns some kind of mode switching to a particular key on the keyboard. The problem is when we're working in AR and VR, we usually, if we have any spatial input devices at all, they have something similar to these old school controllers, very limited number of buttons. So the more common approach is to adapt 2D menus to the 3D UI world. Some considerations here that you should think about is occlusion. If you bring up huge menus, they might actually occlude the underlying task and might annoy or not allow the user to perform the task that they're after. So that brings us to Manu Placement. So, and I want to show this really quick video from this is a social VR game called Rec Room. They have a really nice adapted 2D menu approach. So let me see.
All right, let's talk about the watch menu. Now, you probably know that if you look at your wrist, you're going to get your watch menu. It'll come up on either wrist. You can use it on either hand. And then you're going to use the other hand, bring up your laser pointer. You can step through everything. You're going to get where you need to go. So that's the basic watch menu. But here's a trick you may not know about. So if you bring up your watch menu like normal and then hit your menu button, it's going to detach. That's no longer stuck to my hand. So that means I can move around. I can use either hand. And what's kind of cool about that is I can bring it up and detach it. I can use that same hand to operate the menu. So if I've only got one controller for some reason, no problem. I'm going to detach the watch menu and use it that way. All right, that's your watch menu. Check it out and have fun.
So this is a very powerful way of giving the user the options to move these menus around because they just take up so much space in the field of view for your user. It's surprising if you make the assumption that you can bring in menus from 2D UIs to 3D UIs. It just doesn't work that way. Another quick demo I wanted to show is for symbolic input. This is also quite an active field, a very popular topic for course projects in my spring course. It's to think about how do we actually enter text in these 3D virtual environments. So I'm not recommending this solution, but just to show you what exists out there, there are a lot of implementation, and some of them are quite funny in terms of what we can do. But this is an active research area, and I think we all can relate to this when we have to enter our Netflix password on our smart TV or through Apple TV. It's similar. We don't have a full keyboard, and in 3D UIs, we have other challenges as well. Okay, so we covered all these fundamental 3D interaction tasks. And let's say now we've designed our interaction techniques based on this. What next? Well, according to our life cycle, we go into prototyping. So prototyping the design, this is, again, the life cycle process. It's actually the realization of the interaction design that we were just talking about. We want to create an early representation of the design, not a fully functional system. And then the goal would be here to model and evaluate and then do the iterations and build a more refined prototype after that. Now, I want to go quickly through this. I think most people are aware of this, but for a project like this, the benefits for prototyping, and we've seen this in practice, is to communicate the actual design, what we are designing, communicate this to the stakeholders in the project. And in a project like this, you have domain experts, faculty, researchers, students, and so on. So to create prototypes allows us to communicate product status and so on. Some of the downsides would be if you don't communicate well enough, that some people might think that this is the fully fleshed out product and might be quite disappointed because it's hacky and low poly and so on. So this is something that we're all quite familiar with. Also, prototype fidelity. We have lo-fi. This could be paper prototypes, medium fidelity prototypes, where we have the look and feel of design as we intend to implement it, but only some rudimentary functionality. And then high fidelity prototypes is something that closely resembles the final product. Now, how do we actually create high fidelity prototyping prototypes for 3D UIs, and it's not a lot of options, to be honest. The most straightforward solution would be to use game engines. So we have Unity and Unreal, which are the most popular ones. But we're also seeing now in the last maybe 2 years, platform-specific AR and VR engines that are trying to move the needle a little bit towards medium fidelity prototyping. You still need to code, but it's definitely more user-friendly and more designer-friendly and more friendly to, let's say, designers with non-coding background than the pure game engines. So I'm excited to see actually what happens in that space. And these are the platform companies like Meta is behind Spark AR, Snap is behind Lens Studio, and Apple is behind Reality Composer. Downside here is obviously that the prototypes you build there only work on their platforms. So game engine, if you haven't seen how a game engine looks like, would be the editor view of Unity 3D, which is the most popular one nowadays. And this is some sort of a combination of a 3D modeling tool, if you have used anything like that before. And it's quite complex, and it has a learning curve, even if you are a really experienced coder, or even if you're a really experienced designer. It just takes time to consume it and learn how to use it. There is a heavy coding component to Unity as well, which is done through C#, which is a wonderful programming language, actually. So Unity works quite well, but it is a little bulky and not intended maybe for AR/VR prototyping. I want to talk a little bit about medium fidelity prototyping tools, and I would love if people are interested if they go out and try these tools maybe after this talk. But there are VR tools that we can actually use for medium fidelity prototyping. So tools like Gravity Sketch, Shapes, XR is a new one, relatively new, Microsoft Maquette. So these are all tools where you're in VR and you can start blocking out your interface. So you can start designing your interface. The problem with this is that interactivity is limited. So it's not a high fidelity prototype that you currently have. But let's think about what we have for 2D UIs. We have something like Figma, InVision, Sketch, which we would probably call medium fidelity prototyping tools, right? I think we will see solid medium fidelity prototyping tools in the near future. It might end up being something similar to the platform-specific engines. Now, related to this is prototype interactivity. I want to go through this quickly here. So if you're working with a medium fidelity tool, as we saw on the previous slide, you can actually say, okay, well, I'm just working within a specific interactivity prototyping category. Maybe everything is scripted, or we're doing Wizard of Oz prototype, because you can actually have multiple users in some of these tools. So there are some really interesting prototypes you could do without ever writing a single code. Just keep that in mind. Okay, recap. We talked about human physiology, perception, different techniques, and so on. We only talked about design stage and implementation stage. Obviously, you do evaluation, especially in research and also in industry. You might do more of a feature-based evaluation for your product, and so on. I want to end this with some maybe good segue into a short Q&A. What is going to happen in the near future? Hopefully in the near future. Eye tracking already exists, especially on the higher end AR head-mounted displays, not as primary input signal, but something that allows us to create more advanced interaction techniques, something that can add on to the other signals that we have. There is a lot of interest in adaptive interfaces that try to know the intent of the user before, let's say, I select an object, because we're tracking the eyes, we're tracking the head pose, and we might be running some advanced models that will tell us it's quite likely that the user is interested in that red object right in the center of these cluster of other objects. And then also new input technologies. I didn't really talk about that, but what we saw here was primarily focused on the traditional handheld spatial input devices or hand tracking, but there is a lot of activity, and has been for a while, in brain-machine interfaces. So all the big platform companies have made some large acquisitions, and of course there is research activity in the academic community as well. So taking all this together, we're going to see much more machine learning driven interaction techniques in the near future. So what you saw here was a little bit of an old school approach to 3D interaction design, rule-based, but as we get more input signals, as we get more data, as we get more powerful standalone devices, this is going to enter more kind of computational interaction. It's quite exciting. So with that, just a list of references. And I'm not going to list my collaborators, friends, students, and so on, but you can find all of them and all our projects on our website. And with that, thank you very much.
Thanks, Harold. I think we're going to try to do some sort of hybrid online, in-person question asking. Does anyone in the room or online have questions? I would type them into chat if you have them online. Or does anyone have anything here? Can I pick a fight?
Yes.
I saw in the end you were talking about Wizard of Oz interaction pro techniques, and I saw that the first word that you wrote was deceptively.
Okay. Fight.
Okay.
I know you've done
yeah. That's
good
exactly.
numbers,
Yeah,
so
right.
you win.
No, but I mean, I think but maybe the question is, do you like, what are the kinds of prototyping techniques that use deception, and when is it good to use, or when is it bad to use, or like, what are your concerns about it, and how would you use that if you did?
Well, I think the word there may be, the classic example for Wizard of Oz would be if you don't have the tools to implement, let's say, speech recognition, you have a researcher, let's say, inside the virtual environment, not rendered in the field of view of your participant, and the participant might say, move this, put that there, and then you, as an invisible Wizard of Oz, you could just move that. So the wording could be better, but that's what we
right.
refer to.
But when do you think it's okay to use and not okay to use?
That word?
Yeah, no, just Wizard of Oz.
It's I think it only matches certain conditions, right? For speech recognition, it works fine. If you go into rotation, manipulation, you still would have to implement that anyways for the person who is doing the manipulation. So why not give that to the user? I always think about Wizard of Oz for something like speech recognition, and we've used that in student projects in my course.
Okay. Michael Choice asks online, he says, awesome lecture. My question is, with respect to the motion sickness component of the VR movement, what are some new techniques that are being developed to mitigate this besides from teleportation?
So there's no new hardware. There's not anything close to consumer level, but the software-based techniques are usually you can reduce the amount of optical flow. That is the most important thing. If you have strong optical flow as you move in the periphery, that is not great. Then you're getting a really strong signal of movement through the visual senses. If you could limit that or reduce that optical flow during that moment when you're moving, that will really reduce the risk of vection. And how you do that is the classic techniques would be to put a temporary vignette as you're doing this continuous movement, or maybe blur it. But also this really relies on the environment. Like if the environment has detailed texture, then it will create optical flow in the field of view of the user. And if it is nearby, then you have like a stronger vector field for that. So, but the thing is, it's based on the individual. So ironically, I'm very sensitive to sickness, much more than most of my students. So some of my students, they try out these applications and they're running their own studies that have something to do with travel, and they're fine. I'm not so lucky. So it's very different from one person to the next.
Yeah, I agree.
And I remember when I tried your simulator, I got sick even in that sitting in the car a few years ago.
Yeah.
Yeah.
I also get sick. I
Yeah.
have one pilot a day. Oh, Jenny. Sorry, I didn't see the hands up. Yeah.
Thank you. Thanks for the really excellent lecture, Harald. A really amazing overview. I have a question that pertains to how these Exart technologies are being used in architecture. And as you know, for a while now, they've been used as a representational tool, right? So the architect wants to share with the client what through VR, what their commission space, building, et cetera, may look like. But some of the more interesting developments, which Professor Leslie Locke presented, I know in the monthly meeting recently, use AR to assist with the construction process, and especially in situations where the build is fairly complicated, and or for example, the design process is much more integrated with making and considering how the design can evolve through making and construction. And I'm curious if you have been approached, or if you're working with anyone, even people in the construction industry that are interested in bringing these technologies into their process and thinking.
Right. So this sector, this AEC, architecture, engineering, construction, is, for example, what the game engine companies have been looking at, and AR and VR is one part of what they're looking at for that particular industry. So historically, it has been about visualizations. You're able to put your client, if you're an architect, you're able to put your client into the building using a VR headset, get much more immersive sense of how things actually would look like instead of looking at it on a 2D screen. What you mentioned for AR, that definitely exists for mobile devices, but it's still, this device is great, but it's just such a tiny little portal into this, and you would only see portions of the building that you're looking at. Even with an AR headset, you would have a limited field of view. What I think is interesting in this sector is collaborative design tools. There are a few startup companies in this field that are looking at where designers can basically look over, let's say, a city map, and you can start prototyping different buildings together. You can change the height, you can change your viewpoint, you can zoom in and go in on city level. So think about Google Earth, but you're able to create gray box buildings essentially. So I think that is really interesting. Archeo is a company that you should take a look at. It's quite interesting in that field.
Maybe more, and then we have great questions.
Thank you.
Thanks, Harald. Great talk. Question. So now that we have a dinosaur eating our tree, what do you think will be technically possible in 25 years from today?
I try to stay away from these predictions, but I mean, everybody is hoping that we will have maybe in the next 5 years, 10 years, who knows, AR glasses are like in the form factor of the glasses that we're using right now. The path towards that might be more first with smart glasses, so not full 3D tracking, but some overlay. I'm hoping that we'll like in an ergonomics point of view, we get much smaller devices. Even for me, who is obviously very interested in this field, it's still a burden to put on a headset. Like if I go home, I am more likely, if I just want to relax, maybe to pick up a PlayStation controller instead of putting on a headset, because it's still bulky, it still pulls you out from the field. So I don't know, it's impossible to say in 25 years. Maybe we're still looking, maybe the dinosaur will actually eat the physical trees. So how about that? There's some kind of
Like it.
nano miracles.
So Uli asked, you got really interesting talk actually. Uli says, but he's not familiar with the technology at all. So great introduction. His question is about what the drivers are for VR. He gets AR and he hears meta statements about the future being in VR, but somehow he's just not convinced. And can you help?
What are the drivers for what? Sorry?
VR?
Like use cases?
Mm-hmm.
Collaboration, gaming. So currently gaming is the way you would monetize content in VR. I think what we're lacking right now is just true utility applications, which you check in every single day. You either connect with friends or you do something. We're still a little bit in this era when I feel when computers were not connected online, you would have like a singular sessions and you would not have this utility before the internet came, even though these devices are obviously connected to the internet. So I would say collaboration and entertainment for sure. Consumption of information.
Consumption of information. Great. Any other? Frank.
Great talk. Thank you. I learned a lot.
So you mentioned a lot of like 2D interactions and how like 3D interactions are based on like 2D principles. Like one thing about when the 2D principle like is like they have feedback. So for example, when you hover a mouse on button, your button can change color. So I'm wondering like what are some new like feedback mechanisms that are allowed by 3D interaction, and like if any more or any less, because I realize when I interact with like 3D interface, I actually kind of require more feedback, because if my hand is somehow in the middle, I'm not really sure like what I'm interacting with. So I actually require more feedback. So like what are your thoughts on that?
Yeah, exactly. So it's a great question, because when you build, let's say if you're building an interface or building an experience, you need to think about, for example, visual feedback and depth perception. If you don't have shadows enabled in your application, or you're using unlit surfaces, depth perception might be completely off and you're not sure where your hand is relative to other stuff. And also just in terms of putting texture on planar surfaces, because monocular depth cues are important even in stereo experiences like VR. Other feedback, you just go across the senses. You want haptic feedback as well, auditory feedback. Haptic feedback is certainly more important and more available in 3D UIs, as long as you have a physical spatial input device, than when you're writing on a laptop or using your mouse to. So the feedback dimensions there are more of them than for 2D UIs.
Thank you so much, Harold. I will wrap up by pointing out that Jenny has posted in the chat, and maybe she can repost that this and the previous Design and Tech, what is Design and Tech, lectures are available online in case you missed them, or you want to show somebody else something really cool that happened in this lecture. And I hope that we will get a chance to do another series come fall and keep asking this question of what is design and tech and looking at all the different ways that we could be doing that. Jenny, is there anything else you wanted to say in closing?
Only just thank you, Harold. Really fantastic lecture. And yeah, I encourage those of you that are in person and online, if you weren't able to attend the previous three, they were all just really incredible talks. So please visit the recordings. You can watch them at your leisure. And we look forward to engaging you in the fall, and we'll be in touch.